Hey, welcome to The Explainer. Today we're going to pull back the curtain on something pretty cool. How do machines find hidden groups in just giant, messy piles of data? We're going to dive into a classic, super powerful algorithm that does exactly that. It's called k-means.
All right, so let's get right into it. The world is just swimming in data, right? But what happens when that data doesn't come with neat little tags or labels telling us what it is? I mean, how do you even begin to make sense of all that?
And that is the central challenge right there. Seriously, imagine I handed you a key to a library, but inside, none of the books have titles. They're not sorted by genre. It's just a massive, chaotic collection of text. That's pretty much what a machine often faces, pure unstructured information. Its job? To find the hidden structure, the secret categories, with zero help from us.
And you see this stuff everywhere. Think about it. A search engine has to figure out which of its billions of web pages are about sports versus, say, finance. Or take Netflix. They use your viewing history to lump you in with similar customers. And that's exactly how they decide what movie to recommend next. These are all just huge, unlabeled piles of data, waiting for an algorithm to come along and find the patterns.
So, how do we do it? How do we tackle this mess? Well, we use a special technique from a branch of machine learning called unsupervised learning. And that's all about finding patterns without any predefined labels. And, a real star player in this field is k-means clustering.
Okay, so at its core, clustering is really just automatic group detection. The whole point is to make the groups, or clusters, as tight and distinct as possible. So everything inside one group should be super similar to each other, but really, really different from the things in all the other groups.
And k-means. It's probably one of the most famous and, honestly, intuitive ways to get this done. It's a fantastic starting point if you want to understand how machines can chop up data into meaningful groups completely on their own.
So, what's the end game? Well, k-means has a super clear objective. Imagine each cluster has a center point, kind of like a capital city. The algorithm's whole mission is to place these cities and assign all the data points, the citizens, to them in a way that makes the average commute for everyone as short as machinely possible.
Okay, that all sounds great in theory, right? But how does it actually work? Let's walk through the simple, kind of elegant process that k-means uses to find these groups.
Believe it or not, it really just boils down to a simple four-step loop. You initialize, you assign, you update, and then you just repeat. You do that over and over until the groups are stable. Let's break each of those down.
Okay, step one. First, we have to decide how many clusters we're even looking for. That's the k in k-means. Once we pick a number, the algorithm just randomly drops k points into our data. These are our starting cluster centers. Yeah, it's basically a random guess. But hey, you got to start somewhere, right?
Step 2 is assigning. For every single data point you have, you measure how far away it is from each of those random centers we just dropped. Whichever center is closest, bam, that's the cluster the point belongs to for now. After this step, you've got your first pretty rough draft of your groups.
Now, step 3. This is the clever part. You look at all the points that just got assigned to a cluster, and you find their average location. Their center of gravity. Then you actually move the cluster center to that new spot. This is the mean in k-means. The center just got a little bit smarter, a little more representative of its members.
And here's where the magic loop happens. We just repeat those last two steps. Now that our centers have moved, we do the whole assignment thing all over again. Every data point checks to see which center is now its closest neighbor. And yeah, some points might totally switch teams. Then, of course, we update the centers again based on who's in the group now.
So this cycle of assigning and updating just keeps going, and with every pass, the clusters get a little bit better, a little more refined. But it can't go on forever, can it? So how does the algorithm know when to stop?
It's actually pretty simple. It stops when it hits a point of stability. Eventually, after an update, it'll go to reassign all the points, and nobody moves. Not a single data point changes which cluster it belongs to, and at that exact moment, the algorithm knows it's done. It has converged. The groups are locked in.
Now, as elegant and cool as k-means is, it's not a magic bullet. And it's really important to get a handle on a couple of its key limitations so you can use it well.
Okay, so there are two main challenges to keep in your back pocket. First, remember how it starts with a random guess? Well, because of that, you can actually get different final clusters if you run the whole thing multiple times. To get around this, people have come up with smarter ways to start, like a method called k-means++, which helps pick better starting points. The second thing is that k-means makes what we call hard assignments. A data point is either in cluster A or cluster B, period. It can't be a little bit of both. And that can be a problem for data that's kind of sitting on the fence between two groups.
So, you might be thinking, with those challenges, why is this thing so popular? The answer is simple, because despite its simplicity, its ability to find structure in unlabeled data is just incredibly powerful in the real world.
And this is where it really hits home. This stuff affects you every day. It's used to create the customer segments that decide which ads you see online. It's the thing that automatically groups news articles by topic on your favorite websites. It can even be used for what's called novelty detection. If a data point is just way out there, far from any cluster center, the algorithm flags it as an anomaly. I mean, think about that. That's a system that could spot a fraudulent credit card transaction or a faulty engine part before it turns into a huge problem.
You know, this quote from our source text really nails it. Machine learning, and especially unsupervised learning, is fundamentally a search for these hidden relationships, these non-trivial dependencies, and clustering is one of the main tools we have for digging them up.
So, the next time you get a recommendation on Spotify or see your customized news feed, just take a second to think about the algorithms humming away behind the scenes. They're constantly clustering, sorting, and trying to make sense of a chaotic world of data. And it really makes you wonder, right? What unseen structures, what hidden groups are quietly shaping your world right now?